Uh-oh, it's Jeremy Wolfe.
Was that it?
No, I'm just waiting. I'm waiting for you to be ready. So next speaker is Jeremy Wolfe. The title is, Uh-oh. Does 40 years of visual search research actually tell us about visual search in the world?
Okay, well, thank you, Ruth. Where's that? Why are we, for some reason, we have decided to be halfway through the talk here. Let's try, yes, thank you. Now we're nowhere in the talk. Okay, that seems good. That looks like visual search. That seems good. All right, so this is a visual search session. Here is, all right, there must be a reason why it doesn't want to advance the slides either. There we go. Here's the start of a typical visual search task. You would announce, I think you used these words, Shay. The visual search is ubiquitous in the world. But unlike Shay, then you go on to say, oh, well, we can't really do this in the world. Let's bring this into the lab. And then you do the demo. So clap if you find a T. Good, thank you. And then we collect, then we can't spell the word present. And we collect decades of search data. And what? There's the T. That's very good, yes. I'll be here all week, folks. So we collect lovely data, and we produce lovely models, whatever they said yesterday. Note that almost all of this is based on blocks of trials, typically. We run the search for the T for a few dozen, few hundred trials, and that does indeed capture a number of real-world important tasks here, for instance, baggage screening at the airport or something, where you do the same thing over and over again. But that's not actually typical. If you do a block of 200 Ruth Rosenholz searches, that's called stalking. And if you do 200 Lysol searches, that's called OCD. Real world, typically, is something more like this. And in fact, this is, if you were here for the first talk in the session, I'm basically recapitulating Shay's talk here. There are, the question we want to ask today is, does this matter? Does it matter that the data that we've been basing an awful lot of our search work on comes from blocks of doing the same thing over and over again when the world is based on doing different searches on trial to trial? Now, it is the case that there are lots of real-world search tasks. In fact, we have studied real-world search tasks that we've sort of picked because they have the trial structure of the real world. There's an awful lot of the medical image perception work is done on screening mammography because, oh, look, they do blocks of 200 trials for us. How convenient. But what happens if you move to a setting like this, radiology in the emergency room, where the doctor's looking at a head CT and then moving on to an X-ray and then moving on to an ultrasound or something like that? So that's the question for today. Does it matter if you have blocked or mixed trials? Now, I should quickly say that there are certainly cases, lots of work in the literature, probably including from a number of people here, where you do change the target on each trial. In fact, that's what Shay was doing. What I'm specifically interested in doing is looking at the sort of classic search data and seeing whether or not those data change if you mix up the tasks rather than having them blocked. So let's take a collection of different tasks. that are going to be the sort of standard things. We'll do a whole bunch of feature tasks first. So, here's a color feature search, and here's a lighting direction search. That's a little bit harder. That's the target. Here's a different lighting direction. You're looking for the cube that is lit in a different direction or oriented in a different direction. And here's a nasty feature search, but I wrote about it years ago, so I threw it back in. Vernier offset is detectable in parallel, pre-attentively, but it's hard, particularly if you mix things up. So we're going to compare the standard situation where you do, in this case, 100 trials of one task in a blocked condition to a mixed case where we randomly intermix the same sort of tasks. We ran the blocked condition first in this experiment because we didn't want to give we wanted to give people some practice with the tasks and see what happened with it. It wasn't the right decision. We'll come back to that. And in the results that I'll be showing you, I'll maintain the convention that solid lines are blocked data and dashed lines are mixed data. So what might we see here? We're going to plot the standard reaction time by set size functions, set size on the x-axis, reaction time on the y-axis. And the easy searches will be easier than the hard searches in the blocked condition. We do know how these things are going to come out. The question is, what happens when you mix it? Does the pattern of results change either qualitatively or quantitatively in any fascinating way? And the answer for this particular experiment is that blocked and mixed are really very, very similar. This is the target present data. There are pretty clearly no slope changes in the efficiency of those search. Mixed is actually a little bit faster, but you might strongly suspect that that's nothing but a practice effect from having done the blocked condition first. Here are the absent trials, same story, no changes in the slopes. And if anything, mixed again is a little bit faster, again because of a presumed practice effect. If you look at the errors, there are actually fewer errors in the mixed case, again, probably because of this practice effect. So the behavior certainly doesn't fall apart in any fashion, in this experiment at least, with the blocked mixed variation. In that task that I just showed you, we completely changed the task each time. There are some other interesting blocked mixed variants that we might look at. So if you're doing mammography, for example, you're looking for more or less the same thing on each trial, but the background might that was your talk. You just gave this about changing the background on each trial. I'm actually just repeating what the previous speakers said. So, but here we'll do that with a case where you're looking for this green O on each trial. It can be either an easy color search, a hard color search, or a conjunction search, or a miserable shape search, where in that D condition you're looking for the circle among vertical and horizontal ovals. And here's what the data look like. Again, not much is happening with the difference between blocked and mixed. Again, there's a little advantage for the mix, and again, we ran the blocked guys first, so don't worry about that too much. Same story here on the absent trials. Just for variety's sake, let's look at the errors using D prime, and you can see that nothing's much happening there. So no dramatic differences between mixed and blocked. We did do the blocked case first, which you might think was which was a bad idea. It really did seem like a good idea at the time, but it might have just polluted the whole result by teaching people how to do the mixed case before we did the mixed case. So why don't we just do a pure block of mixed? We'll just run a bunch of subjects, only mixed. We won't teach them nothing. And what those data look like is you can't really see them. They're the asterisks. They sit exactly on the other mixed data. There's no effect here of having a pure mixed case doesn't suddenly cause our subjects to do anything dramatically different. Same in the target absent trials. It's really striking how those mixed trials sit right on top of the other mixed trials. So no dramatic difference between mixed and blocked. Running blocked first isn't why we got the particular results we do. We'll quickly do one more version. This time we'll have the same scene but different targets, so you can try this out yourself. Clap if you find Pringle. Yeah, that's good. Clap if you find a brown bag. Clap if you find a dog. Yeah, somebody's hallucinating a dog. So we'll do it with a much more boring scene here, where we'll have these things in the background all the time. You can look for a conjunction. You can look for, oh yeah, that's it. That's not a dog either. This is a nasty orientation search. Yeah, there it is. This is its easy friend. And yeah, that's easy. If you don't get this one, you need help. And we also threw in a condition where they were all, it could be any of them. And here what we're doing is plotting the mixed data against the blocked data. So the diagonal line is the line of it's all the same, and you can see that basically it's all the same. One last point before this is just a negative recitation. Oh, clap if you find clap if you find the T. Good, you clapped. No. Okay, tried this one. Oh, that's got a T in it too. How boring. This was supposed to be a blank trial. The question is, how do you know when it's time to quit? So, going back to, I think this is 1990 or so, 1996, we and a variety of other people have proposed that the way you know when to quit a search is basically by an adaptive process where you get a little faster if you get the answer right, and if you get the answer wrong, you get slower. We get a nice replication of that in the blocked data, but there's no replication of that in the mixed data. And I think the most significant result here is that this really casts into question how it is that people know when to quit. The idea that you're quitting because of an adaptive process over many trials in the experiment, I'm thinking, is probably wrong. What you're probably doing is adapting over a lifetime to learn when a scene comes up, when is it time to stop looking for a dog. And I see a little red light, and I'll stop.
I think we have time for a question.
Dominique is back.
Yes, you're our questioner this session.
I was wondering, when you look at this, did you look at the last instance of the same task to see whether an error
On the previous task bounced up? Yes and no.
So not only the last trial, but the trial.
So, I mean, the analysis that Dominique is suggesting is that I should look not just at the previous trial, but at the previous instance of that task. The answer is we didn't see a significant effect, but we're vastly underpowered to really look at that.
I think you could take one more.
Yeah, I think another question I'm curious about is that a lot of our searches are relatively unique, so we don't have 100 trials, searching for the same thing, either blocked or mixed.
Yeah.
And I'm just, if you look at like early trials, do you see similar patterns? Obviously, it's harder to do it numerically, but
Yeah, we're sort of underpowered for that too. There was no particular evidence of an effect of where you were in the 400 trials of the whole experiment in the mixed case. This is a problem. Shay's lovely experiment before with the shopping has the prospect of having a different thing on each trial. That's great, but then you can't average across hundreds of trials. I haven't quite figured out how to beat that. Are you going to let Adam talk? No.
Is it quick, Adam?
Never.
Jeremy, you remember in our entire Santi, we did an experiment where you did oddity search or feature search on every trial versus the blocked, right? So with feature search, you get one set of data, and with oddity search, you get a very different pattern when you add more distractors. And we found some subjects could switch with no cost. And the other ones were so bad that they just picked the worst strategy and stuck with it all the way through. And we did this for about 3 months, and we couldn't get the bad ones to figure out how to do the mixed trials. So the task in oddity and the task in feature search is so different. I believe that everything you've done is a feature search of one sort or another. So I
They
would really
weren't all
love to see
feature
you do
searches,
this
but-
with oddity as another possibility.
Yeah, no, it's,
We had a very short time for a question there.
yeah. And that's an Arnie Christensen foraging question. He'll answer it.
All right. Thanks again, Jeremy.